rotation matrices act on a three-dimensional vector, and the operation can be written in this by giving can be given by this Rodriguez formula, which is stated as this. Under this approximation of small angles, okay, where your theta or the angle with which you rotate about some axis n, right, that axis is denoted as n vector over here, and about that axis you rotate about theta. If that theta is infinitesimal or very small than 1, very small than 1, then this can be approximated. This cos theta will be equal to 1, so this term will vanish and sin theta will be equal to theta, right? So this under this Rodriguez formula, an infinitesimal small angles, this rotation matrix, the operation of this rotation matrix on a three-dimensional vector can be summarized in this formula. So you have this higher order correction, which is basically all the terms which are more than theta square, the contribution from all the terms more than theta square, and under this small angle approximation, those all terms can be neglected. The contribution from those terms can be neglected. Okay, so in general, like this cross product of this n vector with any vector, three-dimensional vector, can also be written as some matrix operating on that x vector. Okay, this can be replaced by this matrix operating on the x vector, and then this R can be written as some identity operator minus I delta theta into this matrix, which basically represents this n cross. Okay, so I have taken this x vector out, and all I am left with is the formula for this rotation matrix. Okay, we know that basically these rotation matrices should be orthogonal, right? Orthogonal means a matrix is orthogonal when for say A you take matrix R to be orthogonal. R into R transpose should be equal to identity, right? So if this should be valid for say you can neglect these high order terms, then under that assumption R into R transpose should be equal to 1, right? Identity. So this should be valid. Okay, if this is valid and I can expand this term, right, this RHS, if I expand I will get like 4 terms, right? So identity minus these 2 terms, which are basically this into identity, this into identity, these are these 2 terms, and the 4th term will be this term into this term, which is basically ordered theta square. Okay, and under the assumption that theta is infinitesimal, I can neglect this. Okay, so this whole thing is basically equal to identity. Okay, that's what we started off with, which is basically the definition of orthogonal matrices. If I equate this with identity, and this is what we obtain, then one can see that you can cancel identity from both the sides, and you are left with J equal to J transpose, J equal to minus J transpose. So that is a definition of anti-symmetric matrices. So we say that the matrices which generate rotation, right, under Taylor series expansion, if R can be written in this form, these J's should be anti-symmetric. Okay, cool. That's what we derived. Okay, now we know from limit, like these theorems in limit, right, real analysis, that if P here goes to infinite, right? If P here goes to infinite, I can approximate the limit of this thing goes to exponential of x. Okay, so using this I can further write this thing. Okay, if I if I in succession I multiply a lot of R matrices, so that I rotate in small chunks. Okay, and the resulting theta should be basically delta theta, like you are operating for say you are operating delta theta p times. Okay, that will result into a finite theta, right? So that can be represented using basically multiplying rotation matrices corresponding to delta theta p times. Okay, so that's what I have done here. So if you multiply p times those matrices, so that will be equal to 1 times of minus delta theta j, okay, in p times, right? So that will be 1 plus j to the power p, delta theta j to the power p, and that can be written as exponential of that whatever the argument was. That is what this is. Okay, cool. So this is basically this is what we say J is generating any general rotation matrix along. So this rotation matrix is basically rotating any three-dimensional vector along for say you want to rotate a three-dimensional vector along some direction n. Okay, n is basically a three-dimensional vector. You want to rotate that three-dimensional vector along this about this n with some angle theta, right? And that can be represented by this. And you must have seen these rotation matrices. There are many representation of these rotation matrices in terms of Euler angles. So and many other also. So this is one way to generate these rotation matrices. And these J's, we saw that it should be anti-symmetric. Okay. Now for say you know the formula for a rotation about z-axis, right? So that is this rotation about z-axis. This is the famous formula for rotation about z-axis. And if I use this, okay, and I plug in our formula for here, right? So this matrix we know for rotation about z-axis, right? And this should be equal to I minus some j corresponding to the third axis. For say you want to rotate about third axis, and what should be the j corresponding to that? That we can find using this. Once we know this LHS, which is basically this formula, we can substitute in here, right? And this R should be equal to this matrix minus identity by theta should be equal to this j of c. So these are called the generators. Okay. Okay. I will talk more about what exactly this generator term means. Okay. So using this thing, I can find basically what should be j of x under this limit theta equal to 0 tending to 0. I can find what is j of z. There should be I here. What is j of z? You can find to be this. Similarly, if you know what is the rotation about x-axis, you can find j of x corresponding to that. Like the generator which should generate rotation about x-axis. Similarly, you can find generator which generates rotation about y-axis. Okay. So till now what we have understood is what is this rotation matrix. Okay, this rotation matrix is basically element of SO3, as we call special orthogonal groups. Okay, so these rotation matrices should have the determinant equal to 1 and they should be orthogonal, right? And what we saw here was this can be represented in this form, right? You can write any general rotation matrix in this exponential of this form, and this is basically called, these J's basically form a part of the tangent space to this group. What I mean by group is all these rotation matrices in themselves form a group, and this group is basically a mathematical entity, right? So they have some properties like set or like vector space. You have something called group, and they have some axioms that they should satisfy, and these rotation matrices actually form those actually satisfy those axioms, and they form a group, and that group is basically what we call as SO3. Okay, and that group, you can imagine that as a manifold, and you will have to a manifold you will have basically a tangent space. Okay, these J's lie on that tangent space. Okay, these J's are basically vectors on the tangent space. Okay, and these groups are these groups will basically be differential in nature. Okay, and so yeah, and these differential groups are basically called these are a fact basically. These are called Lie algebras. Lie groups. And there is a rich structure to it, and these J's, the tangent space to these Lie groups, are called Lie algebras. Okay, so these J's are basically part of the Lie algebras, And these Lie algebras form this commutation relation, this famous commutation relation, that Jx Jy should be equal to I Jz. Okay, and these Jx Jy Jz are basically the generators corresponding to x, y, and z, rotation about x, rotation about y, and rotation about z respectively. Okay, so these are kind of the basis vectors in the tangent space. Okay, Jx is the basis vector, in Jx, Jy, and Jz are basically the basis vector of the tangent space, or the Lie algebra of this SO3. Okay, I can you will have more such relation if you plug so Jy and Jz commutator will be I times of Jx. Okay, if you combine all of these, you can write overall commutation relation in this form. Okay, where you have Ji Jk equal to I times of epsilon Ijk, and this epsilon is basically called as a Levi-Civita symbol. Okay, so it has a nice property that epsilon of 1, 2, 3 will be equal to 1, and if you permute it evenly, right, it will be equal to 1, but epsilon of 2, 1, 3 will be equal to -1, and if two of these indices are equal to each other, then epsilon